Hi guys, Mr. Johnny here. This video is gonna be another experiment of mine. I just went... This battery doesn't have anything to do. This experiment is about a ZVS induction heater and a tip on a stick. That's a tip, just a generic tip for a Heiko 900M series irons. As you can see, quite a big one. And I use it on these kind of irons that I got off of eBay. It seems that, I don't know, is it original or not? Seems too cheap to be original, but the heating element in it is a true ceramic heater. It's not just a nylon wire embedded in ceramic. It is a thick film ceramic heater. Seems to be alright. And the cord is silicone. It's nice. It doesn't burn with a... It doesn't burn. Insulation doesn't burn if I touch it with the tip of the iron. It's pretty nice. So what I have here is just a ZVS built on two IRF Z48 MOSFETs, and they are basically just a bit beefier versions than IRF Z44. So, as you can see, the work coil here. You can see the choke there and a resonant capacitor there, six of them, because they see quite a lot of current going through them. And yeah, the funny thing about it is that the part that heats up the most here is the capacitor there, the resonant cap, and the actual coil. The coil is, well, I wouldn't say it's wound with a thin wire, but for currents this wire sees, it is quite thin, to be honest. It is quite thin. So yeah, in a proper induction heater, this coil is made not really of wire. It's made of copper tube, through which a coolant goes through, circulates through, and cools it down, which is pretty awesome. But just a little prototype that I cobbled together to test the concept, because I liked seeing how good these induction irons are. So what I'm gonna do is I'm gonna take a solder, I'm gonna stick it in the middle of the coil. It's not ferromagnetic, it does not heat up on its own. So I just gonna put it there so we can see how much time it takes for this tip to heat up to the temperature. So let me do just that. Okay, the tip is completely cold. No burn marks. Power supply on. See, the solder is not melting because it won't. I'm gonna dunk the tip in there and you count for yourself how much time it takes. Okay, here we go. I measured it previously at about 30 seconds. It's very hot at that time, so... I can feel the heat. There we go. It's melting. Another ball there. You can see it's molten pretty good. Make more smoke so it's much more. Heat it up a bit more. Awesome. 30 seconds up to full temperature. It's pretty schmick if you ask me. I'm gonna turn on the fan there so the capacitors cool down. This piece of cardboard is there so the air is not blowing on the coil, which is kind of bad actually because it heats up, but I put this deflector in there so it doesn't heat the actual piece I try to heat up. So it doesn't cool down the actual piece I want to heat up. That's what I'm trying to say. The problem is that I can't really make an induction iron with it, because an iron should be a slim handpiece, right? And if I'm gonna put a coil there which is center tapped, so it's pain in the ass. Plus I'm gonna need to put the resonant capacitor somewhere close. Not great at all. Plus, as I mentioned, this thick wire heats up quite a lot. So imagine what will happen with the wires inside of a flex, or inside of this cable. They are gonna just heat up so much they're gonna melt together and cause you catastrophe. So yeah, this coil just carries too much current to be implemented as a iron. You can dunk an iron in there and heat it up. It will work. My point is that unfortunately you can't really make a soldering iron with that. Plus the feedback is gonna be quite tricky. Because the ZVS is self-running oscillator, which you can potentially be kind of control. See those resistors there? They are joined in one place there, see, on a positive of that capacitor. You can break that point from the capacitor and put a high side switch in there. And basically by controlling the switch you will turn on and turn off this oscillator. You don't have to do it very fast. It can be as you can actually maintain temperature roughly by just turning on and off the oscillator, which is a PWM of sort of, which is not a it's not a PWM because you're not changing the duty cycle. Basically what you're doing is that gating an oscillator, I guess it's a correct term to use here. If the tip is cold, you turn on the oscillator. If the tip is too hot, you turn off the oscillator, and you kind of try to keep the temperature within the desired point. But again, it's pesky with this center tapped coil which heats up and stuff like that. I think in stations like ERSA or so, or Metcal, they're using a higher voltage at a lower current. That's how they get a good power. That's how they send a good power through the cable, and the cable does not melt in there. So they basically using an inverter powered from rectified mains rather than something powered from a low voltage source. My heat, by the way, this ZVS right now is kind of limited because I made it in such a way that it doesn't consume much at all. Right now the current limit is set to about 7 amps on my power supply, and it never hits it. I measured the consumption maximum to be about 4 amps at about 15 volts, so that's only 60 watts of power. So if you take that into account, 30 seconds to heat this up is not that bad for a 60 watt iron. Plus it's gonna be awesome because you won't suffer from the poor contact of the heater to the actual tip, because the tip is gonna be the heater itself. It's like a soldering gun, where the tip of the soldering gun is the actual part that heats up. It's gonna be quite nice, quite powerful, but again, with this I don't think it is viable. I have a hunch that you can use something like TL494 with a gate drive transformer, drive 2 MOSFETs in a half bridge, and then drive the coil from that half bridge. It ain't gonna be resonant though, so it's gonna be quite poor. You can another actual feature of a resonant converter that pulsing the coil with just a square wave will create a lot of EMI if you're gonna send that power through a cable. It's gonna be like a huge antenna which is gonna spit RF all over the place. This thing, by the way, it's a resonant circuit, so the waveform there is a sine wave. And it's pretty clean sine wave for what it is. And the sine wave doesn't have all that rich harmonic content, so it's gonna be quite quiet. Oh, it's gonna be reasonably quiet. So yeah, that's that. Just a little experiment that I decided to do, just because I wanted to do that. So that's it. Thanks for watching. See you.